Thanks a lot. Hopefully you can all hear me okay. So I'm going to try to give you an overview of data-intensive astronomy within the context of Astro 3D, what we're up to, what it means, and so on. And so I thought we'd start with this interesting plots that we saw on the first day in Emma's overview, and we see from time to time in the annual reports, and it kind of gives a sense of where data-intensive astronomy, which I've highlighted in the top right here, fits in across the various projects. And it's interesting to think that it actually connects across basically every major project within the center, which is good. And it also intersects with almost all of the nodes as per the publication database that this is based on. And so this is great, but it raises a question in my mind, which is, what is data-intensive astronomy? And to answer this question for myself, I had to kind of go back to the original proposal for Astro 3D to try to get a sense of context, because I actually think this definition has changed over the course of the center. We've kind of redefined in real time what this actually means. So if we go back to the original proposal for Astro 3D, data-intensive astronomy was seen as this kind of enabling activity, right? Something that helps the science happen across the different themes that the center wanted to address. So it's not necessarily, detecting that highest redshift galaxy per se. It's putting the tools in place that allow those kinds of things and discoveries to actually happen. And this was shown also by Emma on the first day about how it intersects across the actual projects, the actual surveys, observational surveys, and theory surveys that are happening within the context of the center. So that's the big idea for data-intensive astronomy. So that's kind of what data-intensive astronomy is, but who is data-intensive astronomy? This is also a question I had to answer for myself. And so I pulled the membership database for the center, and this is the current breakdown. And so this is people who have identified data-intensive astronomy as an area of interest, a topic of interest, in those forums when you're doing a membership and signing up for things, the people that tick that DIA box. And this is the kind of breakdown. And this is sort of the career stage basis. And you'll notice that the biggest fraction of people who are ticking that box are at the younger end, and the earlier career stage makes total sense, right? But it tells us that those people will need supported in their pathway in exploring what data-intensive astronomy is for them and for their work. And then just in terms of the project affiliation, so data-intensive astronomy, it's not really a science project in itself. So it's usually incorporated with other science themes for the center and surveys in particular. And this is how that breaks down. One can see that galaxy evolution covers so many different bases that data-intensive astronomy feeds into that one mostly, but there's a spread in how project affiliations go. Now, this is only 55 people out of the whatever 300 odd is the full membership, and I expect this is an underestimate, right? I think this is because it doesn't necessarily come up as a science theme for most of you, even though you may be using it, you may benefit from it, and you may have things to say about it, and we'll come to that later in the talk. Okay, so another figure that was shown in the original proposal was this one. The old way of doing astronomy, going to go to the archive on my laptop and I do all the data reduction on my laptop, and then I make some plots in IDL or something like that. And that was the old way of doing astronomy. And we poo-poo that, and we're going to do it the new way, right? The Astro 3D way. And so we defined these different layers, if you like, of data, how data fed into doing the science. Okay, so there's these three kind of areas. It was around, connecting the HPC facilities that we have nationally, bringing in what's called a middleware, which is a very fuzzy term in my mind, but basically connecting up the databases, and then kind of higher level virtual observatory basis where you could not just get the raw files, but you could actually manipulate science products, bring them together in complex ways and address complex questions. So that was the big idea there. Okay, that's great. Now we sit within a broader data landscape within Australia, right? And this is kind of a snapshot taken from the Astro 3D DIA webpage as it happens. And it kind of nicely summarizes in broad brush terms what the data landscape is like in Australia and where Astro 3D fits into that. And so I kind of take these in turn. So I'll start with the Optical Data Center, or as some of you might know as Data Central. Now, that's not strictly an Astro 3D specific funded thing, but Astro 3D connects in with so many things that are funded in different ways. And it's really about how the whole thing fits together. So Data Central, some of you will be quite familiar with this. It hosts a number of data projects and archives for a broad variety of projects. ASTRO 3D specific ones sit there, and there's some key ones here highlighted that we've heard about in great detail, the fantastic science being done by many of these projects. And there's also kind of supporting or related projects that that either used tangentially or lay the framework for other work to be incorporated into this data set or data center in the future. So this is the kind of archive-facing part of what Data Central does, but it's also doing a lot more in terms of facilitating collaborations like what we try to do within ASTRO 3D. So they have a portal that allows you to organize your team, provide services like wikis, data management, sharing data first within your team, then to the broader public, and trying to make that as easy as possible. So this is always kind of a work in development. It's not a big corporation like Google or whatever that's doing this. It's like a couple of people, astronomers at that, trying to cobble this together, but they understand what our community needs. And so I'll give an example here that was also talked about earlier in this meeting around MagPi. And MagPi is this fantastic large program with ESO, super high valuable data. We need to make the most that we can of this, and using Data Central, I think, has been really beneficial to how that project is operated. And this was kind of like the first example of how Data Central can support an ESO program. So you have ways to control your teams and your communications. You can create a wiki to share information. You can share that data as well in a straightforward way through a web interface or other methods. And you can start to run analysis or even data reduction close to where the data sits, right? So you don't have to move these big data sets around all the time for the different steps of getting to your paper. You can try to centralize these things as much as possible. So a lot of these things were kind of ironed out with MagPi, but they're now being applied to the other fantastic large programs connected with ESO and ASTRO 3D that we've heard about in this meeting, in particular MOV and GECKOS, which were mentioned. So this is really a great tool, a great set of infrastructure that's completely driven here and benefits from the connectivity of a center like ASTRO 3D. Okay, so moving across into the radiosphere, how do we incorporate that wavelength or that part of the electromagnetic spectrum? The data are different in many ways, but the science questions are often the same. So how do we bring them together? This is kind of a work in progress. So through the ASTRO 3D efforts, in particular, starting data intensive astronomy and the postdocs that recently started last year, we started some conversations between Data Central and the Australian SKA Regional Centre, Oz SRC, and Karen is, I think, in the room. And that's been a really fruitful set of discussions, problems, and I came in with these big ideas. We're going to do all this stuff. And then we had to kind of ratchet it back to, hang on, let's just compare some tables, right? That's the first thing. And that in itself was like a whole development project, right? How do we actually cross-match catalogs? How can we do this without moving things across the country backwards and forwards? And started some really interesting conversations about how the tools that had been developed independently on one side connected with those tools developed independently on the other, and how they can interact. So small steps, but I'm hopeful that this is going to develop into something that's has broader applications. We start to add dimensions, start with point sources, then we can go to images, and hopefully eventually to 3D cubes and beyond. But there's a lot of under the hood infrastructure that me as a user, I'm not aware of, don't appreciate, but under the hood, there's a lot going on. Okay, and the last one is connecting to the theory side of things. So we've heard, I think, multiple times here about the value of the SimSpin tool, fantastic tool, Kate Harborne's work primarily, and putting that into the public domain through an ADAX project connected with Data Central to host this service. So it's really a fantastic story about how we take theory and we put it in the hands of observers in ways that they can easily access, easily compare to their data, and so on. So a really amazing tool, and yeah, the fact that it's mentioned in every third talk, it tells you that alone. But how do we go forward? It's kind of geared towards doing one object at a time. But we want to answer these bigger sample-based questions, right? So I'm just putting up an example here about kinematic classification. We've heard a bit about that in this meeting. Classic thing, fast and slow rotators. Some of you will know what I'm talking about, but basically it's like, how's angular momentum distributed? How does it evolve with time? These are key questions for ASTRO 3D to address. And we kind of have slightly clunky tools for doing it at the moment. And people have tried to really refine those tools, but still there may be better ways yet ahead. I just highlight here very nice work by Jesse van der Sand about trying to take this to the next level around classification from kinematics. But if we could generate If we could generate samples that we could train machine learning, for example, then we might be able to use full information in a very generalized way and really optimize this problem. The trouble is that with existing IFU data sets, we just don't have enough objects to train the machine learning to do this. Simulations could hold a key, and I'm just going to highlight very, very initial work by a summer student, in the past couple of months, but it kind of illustrates the point here. That we can use SimSpin to do like batch mode, generate samples. So here we're looking at angular momentum versus mass. We can then make random projections of these objects to really fill out the sample in the observed projected space. So here we're looking at how inclination changes the lambda r value, which is that measure of angular momentum. We can use this to train a machine learning and then try to make classification. It sort of works, clearly room for improvement, but it gives you the idea of what you can do when you can generate samples of mocks. Things really start to open up. So I just want to highlight here that we put in an ADAX proposal recently to make this batch mode in SimSpin. Again, that's coming out from the ASTRO 3D collaboration. Okay, I want to come back to this one and say there's actually a fourth one here that is also data intensive astronomy, which is around developing data intensive techniques. And that means different things to different people's. Some people's big data is another person's like small data and so on. But the techniques are the important part. And I'll just highlight a couple of works. I put a mail out, give me some interesting plots. So it's a very biased sample, but it kind of illustrates what's going on within the context of the center. This is another kind of classification fast slow rotator using other labels to predict that fraction and kind of digging into what is the driving relation, what is the causal purpose or the causal mechanism that drives certain trends. And you can do this through, more sophisticated approaches than 1 or 2 dimensional kind of linear regression approaches. I think this plot was shown before around recovering intrinsic shapes from IFU data in a generalized way using machine learning. This is work by Suki Young, who's here, and you can ask questions about. Ivy Wong sent me a couple of projects that she's working on in this space around classification in a kind of galaxy zoo way, source detection in an open way for the vast amounts of wallaby and other radio data that's coming in. So very interesting work done there. In the theory side, connecting up semi-analytic predictions with the n-bodies, this is not trivial, and you want to be able to do this kind of quickly and test scenarios and so on. So this is work by Manadeep Sinha and Adam Stevens about optimizing how we do this kind of infrastructure level things, but it opens up a lot of theory science. Okay, so I'm going to finish up with some questions. I just did a QR code that should somehow take you to a Slack channel I've created. More easy is to wait for me to post it on the general channel after this talk, but I thought this might be a bit of audience interaction. But really, we want to start tackling these questions about, how do we start interacting more broadly? I know there's more than 55 people in the center working in data intensive astronomy. They just haven't maybe seen it that way, but they have things to contribute to that conversation. So bring them in. One example would be like starting to do some monthly seminar series that just focuses on those aspects of the work that's going on here. What's our data legacy? I think this is really important, as we come towards maybe not the, it feels like the beginning of the end, but it's just the end of the beginning or something. There's a Churchill quote that feels appropriate, but what is our legacy for Astro 3D in a data sense? And that's just an ongoing conversation. How do we help future COEs benefit from the experience that we've had? Make things science driven. We have amazing tools. I think we actually have kind of a core now of the tools. Now we need to focus on the use cases, and that's where everyone here comes in. What do you need these things to do? We can connect all these things randomly. That's great, but let's do it in a more focused way. And I think the people doing the development really need that input. So engaging with them in the science questions, I think, is really important. And then what does this look like for those future centers of excellence? And how can we use the last couple of 1 or 2 years of the center to lay the groundwork for that? And I will end there. Thanks.